Evet hocam.
Okay, let's start. Today we'll be studying multiple random variables. First, we introduce joint CDF and then joint PMF. How to derive marginal PMF will be the next subject. And then we'll be looking at joint probability density function and marginal PDF, independent random variables, and how to derive expected value of a function of two random variables. And finally, we'll be studying covariance, correlation, and independence, along with bivariate Gaussian random variables. Okay, joint CDF. You may remember the functions CDF, PDF, and PMF. So we use PMF, probability mass function, for discrete random variables. We use PDF for continuous random variables. Okay, let's erase this. And CDF is used both for continuous and discrete random variables. Now, joint CDF refers to more than one random variables. Okay, joint. Joint means that we have something that is related to one or more than one variables or objects. So when we say joint CDF, so we talk about at least two random variables. Okay, typically this might be more than two. Here we have an example. We have a random variable y. It's written in terms of x and z as a summation of x and z. X is a random variable, z is also a random variable. So summation is a y, which is another random variable. Now we can model this as a system. Let's say a typical receiver, just like cell phone or smartphone, where we have a signal, electromagnetic energy coming from the base station, and this might be defined, let's say an X, and this is the receiver. This is the receiver. It introduces somehow a noise, okay, noise generated by the system receiver. So X enters into the receiver, Z, the random noise is added to X, and then we got Y. So this is a simple model where we have three random variables. This is random variable, this is random variable 2, this is independent from this one, and then we can define a new random variable y, which is a function of x and z. So the properties of x and z will determine the properties of y. Okay, so in that case we can talk about joint CDF. Okay, for example, x and z. This is the pair of two random variables, so we can talk about joint CDF for x and z, x and y, or z and x, z and y, for example. So every two of these will have a joint CDF. We may also define X, Y, Z as joint CDF because joint CDF may include more than two random variables. So this is how to use joint CDF. Here is the description of joint CDF. Let's clear this. The joint CDF of random variable X and Y is written as this, as you see, capital F, X, Y, subscript. These are capital letters, and small xy. These are the values of these random variables. And this is simply defined as the probability that the X, random variable X, is less than or equal to X, any value of X, and Y, the random variable, is less than or equal to Y. Okay? If we plot X and Y, just like conventional Cartesian coordinate system. So we have a range of X on X-axis, and we have a range of Y over Y-axis. So when X occurs, Y might occur too. So we can define a region here. Okay, that's defined for the values of X and Y. Now, probability that X is less than X and Y is less than Y could be a region here, for example, here. Okay, so this could be the region where we define this F, X, Y. Okay, for every X and Y, we can define a region. So simply, joint cumulative distribution function defines a region over XY plane. Here is the properties of joint CDF. So let's write it, joint CDF. Joint CDF is in between 0 to 1. So it cannot be less than 0. It cannot be greater than 1. It's limited to 0 to 1. And when we take X and Y as infinite, then joint CDF becomes unity. And we can define the CDF of X by taking Y to infinity. And we can define CDF of Y by taking X infinity. Okay, so simply we can derive CDF of X and Y from joint CDF of XY. If we define two values of random variables X and Y, where X is less than or equal to X1 and Y is less than or equal to Y1, then Fxy is less than or equal to Fxy, X1, Y1. Okay? We have here. Here, the random variable is defined between X1 and X2, and the random variable Y is defined between Y1 and Y2, and we look for probability of X between X1 and X2, and probability that Y occurs between Y1 and Y2. This can be written in terms of joint PDF. Again, joint CDF, I'm sorry, joint CDF, so F, X, Y. xy. So simply fxy, x2, y2 minus fxy, x2, y1 and fxy, x1, y2 and fxy, y1, x1. Okay, simply again we write x2, y2 plus fxy, x1, y1 and the values of CDF at x2, y1 and x1, y2. Okay, let's see this example 5.2. It's the age of children entering first grade and second grade. X is the years, X years is the age of children entering first grade in a school. Y years is the age of children entering second grade. Now joint CDF of X and Y is given by this formula. As you see, when is X less than 5, it's 0 as expected. The first year student is usually older than 5 years. And for Y less than 6, it's 0 again. When it is, when the X, the age of the children entering first grade is between 5 to 6, and Y, the second grade, is between 6 to 7. So it's given with this formula. It's dependent on X and Y. Now, when X is greater than 6, then the joint CDF is dependent on only Y. It's independent from X, as long as X is greater than or equal to 6. On the other hand, when Y is greater than 7 or equal to 7, X is independent from Y. CDF of joint CDF of XY is independent from Y. It's given in terms of X only. Now find the CDF of X and CDF of Y. To find the CDF of X and Y, we use this theorem. You see, we simply determine fx of X by taking Y goes to infinity. Y goes to infinity means that we have to take the integration of X of U, right? From minus infinity to the value of X. This refers to what? We simply integrate the PDF of, joint PDF of X and Y. Joint PDF of X and Y can be written as the derivative of this. Okay, so in the next slide, we'll be seeing that fxy, xy with respect to X and Y. So we simply take the derivative of this joint CDF and then put this integration to get the CDF of X and Y. This simply taking the derivative of this with respect to Y and then take the derivative of this with respect to X to get the CDF of X and Y. Okay, joint probability mass function. Joint PMF. Again, remember this. We got CDF, we got PDF, and we got PMF. This is for discrete. This is for continuous. And this is for both continuous and discrete. Now we have already defined joint CDF. Next, we define joint PMF. Joint PMF is simply written by capital P and the random variables X and Y. So this refers to joint of X and Y, so joint PDF, PMF of X and Y, which is equal to probability that X, the random variable, is equal to the value of that random variable within the range, and Y equals to Y. Okay, so in order to construct this, we have to insert all X and Y values over the range of random variable X and Y. Typically, this is written as X and SY, which are the sample space of X and Y. And from the probability axioms, we know that the summation of joint PMF over the range of sample space here should be unity. If you are given a pair of random variables, X and Y, and if we define a set B in the XY plane, again, remember this X and Y plane, this is X, this is Y. Now this time this is discrete, so we got samples like this. Okay. So at each point here, we got the value of X and Y. So the range of X here, for example, start from here until here. So here is the range of X. And for the range of Y, we'll look at here. So here is the range of Y. Okay. So this region simply, okay, determines the region of the XY. So joint PMF and the joint CDF. Now we can define here a set B, let's say. B should be, for example, this region where we got 3 values. Okay. Here you see we got 3 values only. So we can define a B here. For this B, probability of B will be summation of X, Y values within this B, the joint PMF over all the values of X and Y. Let's see this in an example. We got the IC test. This is a very common experiment. On each test, we have 2 outcomes, accept or reject. Assume that all circuits are acceptable with probability 0.9. So when I make a test, I got accept or reject. And this says that probability of accept is 0.9. So this is 0.9. Then this is going to be 0.1. So every 10% of the tested ICs are rejected, and every 90% of tests are accepted. This is what it says. Now count the number of acceptable circuits X. So we repeat this successively, and here we got 2 tests. So this is test 1. The next test, it might be either A or R. If the first one is reject, the next one will be A or R. So the experiment could be like that. Again, this is going to be 0.9, 0.1, 0.9, 0.1. So we can determine probability of AA as multiplication of this and this, probability of AR, probability of RA, and probability of RR. These are known from previous examples, as you might remember. Multiplication of this 2 and this 2 and then this 2. We can calculate this. Now we define two random variables. X. X is the number of acceptable ICs. Okay? Number of acceptable. So A here refers to acceptable ICs. And the number of successful tests, Y, before you observe the first reject. Okay, so the number of tests. So A test before the first reject. Okay. So we can define here, for example, our X and Y. In this case, since we are interested in number of acceptable tests, we got one acceptable test and one another acceptable test, so X is going to be 2 here. And Y is going to be 2 because there is no rejection here. Okay, we'll look at the first rejection. Since there's no rejection here, we count the acceptable tests. So acceptable test is 1, acceptable test 2. So the number of tests is 2, and there's no rejection. Then Y is going to be 2. So we can list all this as we can see in the next slide. You see. So we construct this tree diagram. Now we'd like to construct joint PMF. To construct joint PMF, remember the plane again. Here is X, here is Y. Okay, the range of X could be from 0, let's say this is 0, 1, and 2 maximum. So this is 0, 1, and 2. For Y, again, it could be 0, 1, and 2. Okay. Now, we'll try to define joint PMF here. Okay, joint PMF. In order to find this, we look at all the values of X and Y. Here, for example, X is 2, Y is 2, X is 1, Y is 1, X is 1, Y is 0, X is 0, Y is 0. So we got all the values of X and Y here. For example, 0, 0. So this corresponds to 0, 0. What is the probability of 0, 0? The probability of 0, 0 is going to be point, what is it? Let's look at that. That's going to be point 0.1 times 0.1. So 0.1 times 0.1, which is 0.01. So this is probability that you got 0, 0 is going to be 0.01. Okay, so this is 0.01. Next, we look at 1, 0. So 1, 0, so this point. 1, 0 is going to be 0.1 times 0.9. So it's going to be 0.09. Next, 1, 1. So 1, 1 here. 1, 1 is going to be 0.9 times 0.1, which is 0.09. And 2, 2. So 2, 2. So here, which is 0.9 times 0.9, which is 0.81. So this black balls represent the values of joint PMF, okay? Joint PMF. We can then make a table to show this, as you can see here. The joint PMF here for Y0, Y1, and Y2, X0, 1, and 2. For 0, 0, that's 0.01, so this one. For 0, 1, it's 0. It's not defined here, so it's 0. 0. And for 1, 0, it's 0.09, 0.09, 0.81. We can also write that as a function like this. Okay. So we can extract marginal PMF using joint PMF. And for discrete random variables x and y, joint PMF can be used to derive marginal PMF. Marginal PMF, by the way, is simply denoted by Px of x or Py of y. And both can be derived from joint PMF. So we can derive this from Pxy, xy. And also this Pxy, xy. In this example, as you can see, we simply derive marginal PMF for x and y. It's not so complicated. You can easily construct joint PMF by using the table that we have created in previous slide. For joint PMF of x, we simply add the values of the row of the table, the first row of the table, which is 0.01. So this refers to simply Pxy. X is 0 and y is simply 0, 1, and 2. So we add them up to get this. This is the formula, right, we use. Similarly, for x equals 1, we use the second row and sum up all the values here to get the value of Px. So this refers to Px0, and this refers to Px1, and this refers to Px2. Okay, similarly, we can get Py of y, and this is the summation of this first column. This is the summation of the second column, and this is the summation of third column. And this corresponds to Py3, and this corresponds to Py2, Py1, and this is Py0. So once you construct the joint PMF table, you can easily construct the marginal PMF of each random variable. Joint PDF, I have already given an example of this. Joint PDF can be derived from joint CDF. Okay, so it's shown here. We write joint CDF in terms of joint PDF, that's double integration, and then we can get a joint PDF from joint CDF by taking second order derivative of joint CDF. We have similar conditions for joint PDF. Joint PDF is always greater than 0 or equal to 0. It's a positive number. Okay, it cannot be negative. And double integration of joint PDF is always 1. So the area of this joint PDF is always unity. For any random variable pair, x and y, we can define a set, an area, and that area can be probability of that area can be written in terms of joint PDF with this formula. Okay, in the example that we have considered previously, we are given a joint CDF, and we can obtain joint PDF using this formula. As you see, there is just one range there. We got X and Y. All others are either not dependent on X and Y, or it depends on only X or only Y. So when you take the second order derivative of this joint CDF, we can get the joint PDF from this range only. All others will be 0. Okay, and we can take the derivative of X minus 5 Y. I'm sorry. Y minus 6 with respect to X and Y. So we take the derivative of this with respect to X, and then this with respect to Y. Both will give us 1. So your joint PDF here simply constant over this region. Okay, so this region. And all others, that's going to be 0. So we simply write fxy, xy, 1 when x is from 5 to x, 5 to 6, sorry, and y from, okay, let's raise it and write it here. And y is from 6 to 7. Okay, otherwise it's 0. That's quite easy. So if we plot this, here is x, here is y. Okay, for x, 5 to 6, so 5 to 6, and for 7, for y, 6 to 7, so here, so we are talking about here. Okay, here it is 1, all others is going to be 0. Okay, marginal PDF. We can extract marginal PDF using this formula. That's the integration of joint PDF, and here we have an example. Joint PDF of X and Y is given with this formula. Now the question is about marginal PDF of X and Y. To find the marginal PDF of X, we should use this formula. Now we have to know the limits of this integration. To find the limits of this integration, I have to look at the range of Y. So the range of Y here is x squared to 1. So we simply write fx of x as from x squared to 1. And the joint PDF, which is 5y over 4 with respect to y. Since we want to get the marginal PDF of x, we integrate it with respect to y. Similarly, we can write fy of y as integration of, again, the function fy over 5y over 4 dx now what is the range of x here? To find the range of x here, we have to look at these two conditions, right? This one and this one. So x is between -1 to 1 and x squared y 1. So we have to look at the values of y here. Y will be between 0 to 1 because x squared is always positive, so we can take the range of x from 0. That's the minimum value. So when y is greater than 1, that's 0. When y is less than 0, it's again 0. So we look at here, x squared equal y. From this, x is going to be plus minus square root of y. So x will be from minus square root of y to square root of y. When we get this integration, we can calculate marginal PDF of y and marginal PDF of x. Independent random variables. Once you know how to play with joint PDF, joint PMF, marginal PDF, marginal PMF, you can easily understand how or under which conditions two random variables are independent. We always check these conditions. For discrete random variables, joint PMF should be equal to multiplication of marginal PMF of random variables x and y. For continuous random variables, the joint PDF should be equal to multiplication of marginal PDF of x and y. Let's go back to the children's age problem, and we look at the independence of x and y in previous example. You can remember the marginal PDF of x and y here, and you can remember the joint PDF, which was 1. Now we simply check this condition. So this is 1. Fx of x, here it is 1. And fy of y, it is 1. Okay. So 1 is equal to 1 times 1. Then x and y independent. Okay. That's quite easy when the functions are simple. When we get to complicated functions, we have to we have to do some calculation, and this example may require some calculations. You can do that by yourself. Expected value of a function of two random variables. We define a w, which is a function of two random variables x and y. For discrete case, expected value of w can be written in terms of this, and expected value of w is written as integration, double integration of joint PDF for continuous random variables. And for any two random variables x and y, the expected value of x plus y is equal to the sum of the expected values of the random variables. Variance of the sum of two random variables, it can be written as a summation of variance of the random variables plus 2 times expectation of x minus mu x times y minus mu y. Here we define then covariance. covariance is equal to expectation of x minus mu x times y minus mu y. This, for continuous random variables, this corresponds to double integration in x minus mu x, y minus mu y times fxy, xy, dx, dy. Okay, so double integration again. Correlation coefficient can be defined by using covariance. Once you calculate covariance, you can easily calculate correlation coefficient by using covariance and variance of x and y. If you are given a random variable as linear operations of another random variable, the correlation coefficient will be equal, and covariance will be multiplication of the covariance with the coefficients AC. And note that the correlation coefficient is always in between -1 and 1. If we are given x and y such that y equal to ax plus b, then the correlation coefficient will be -1 when a is a negative number. When a is a positive number, it's going to be 1. Here we see how x and y are distributed for different correlation coefficient values. When it is -0.9, we see that when x increases, y decreases. Okay? In the correlation coefficient, when the correlation coefficient is 0, we see that there is no relationship between x and y. X increase, y unsure. Okay? When there is a positive correlation, which corresponds to highly correlated random variables, when x increases, y increases too. So by looking at the correlation coefficient, we may have an idea about how these two random variables are related. There is also correlation, which is expectation of x and y. So this corresponds to, again, a double integration, xy, fxy, xy, dx, dy. Okay? And we can define orthogonal random variables when the correlation is 0. Not correlation coefficient. Correlation is 0, then they are orthogonal. Uncorrelated random variables, the covariance should be 0. Covariance can also be written in terms of correlation and mean values. Variance of sum of two random variables can be written as variance of x and y plus 2 times covariance of xy. When x and y are equal, then the covariance will be equal to the variance of either x or y. And their correlation will be expectation of x squared or y squared. We have also some other properties in here for independent random variables, x and y. And here we inspect the correlation and covariance for the example of IC test. This is very common experiment. And this was the joint PMF, as you might remember, marginal PMF of y and marginal PMF of x. Now determine the correlation. For correlation, we know this formula. This was the form of integration. Now it's going to be summation, since this is a discrete. These are discrete random variables, so we just get the summation. That's quite easy. You can easily do this. You see that the correlation is 3.333. We can also determine the mean values of x and y, which is 1.80, 1.71, and then we can determine covariance by using these expected values and correlation. So as far as I see, this is going to be last 2 slides. here there is an example, which is again the circuit, the receiver problem. We got a receiver, there is a signal X, and there is a noise here added, and we got Y. Y is X plus Z. Okay? And these are independent. Once they are independent, we can determine all the parameters defined in previous slides easily. The covariance is going to be 0, so the correlation coefficient becomes 0. Then we can determine covariance of X and Y, which is expectation of XY, which is X times X plus Z. This refers to expectation of X squared and expectation of XZ, which is equal to expectation, so the variance of X, sorry. The correlation then can be written in terms of the variance of X and Z. Please use this theorem to calculate these parameters. Finally, we have bivariate Gaussian random variable. Bivariate Gaussian random variable involves two random variables, X and Y. Each is a Gaussian random variable with mean value mu X and standard deviation sigma X, mu Y, sigma Y. Each has this marginal PDF here, and the correlation coefficient can be written for this, and they are uncorrelated if they are independent. And here we see how joint PDF looks like for two random variables. One is, you see, this increases, this decreases, so there is a correlation coefficient, probably minus 0.8 or minus 0.9. And here the correlation coefficient probably equal to 0. So here, how they vary. So when I look at the X value here and Y value here, when X increases, Y decreases. While here, when X increases, there is no change on Y. Finally, we got the same problem. Receiver, we got an input signal, X, and noise, Z. They are independent, and we got Y, the received signal, X plus Z. And here, X is Gaussian, so this is Gaussian with 0 and sigma X. So mu X is 0. And for Z, it's again Gaussian, which is 0 mean and sigma Z standard deviation. This is mu Z. What's the joint PDF of F, XZ, XZ? Now, from the definitions, we simply say that the marginal PDF of X is Gaussian, marginal PDF of Z is Gaussian. Then we can define the PDF of Y as a bivariate Gaussian PDF. Okay, these are independent. This makes, you know, this equation simple. Why? Because the correlation here is going to be 0. Okay, the mean values will be 0 here, 0, and this is going to be 0. This is going to be 0, so that we can get this PDF. Okay, you can continue and calculate the joint PDF of x and y for sigma x is 4, being 4, and sigma z being 3. You can easily calculate these values. Okay, I think that's enough. Do you have any question? Any question? Rugesh, Oğuz?
Kulaklıktan ses gelmiyordu da şimdi çıkardım kulaklığı. Benim sorum
Okay.
yok hocam. Teşekkürler.
Okay.
Yok hocam.